The next objective is to determine position from the range and how to associate uncertainty with that estimation of the position. So the range distance is defined by the distance between two objects, and in case of the GNSS, the position is based upon the range between the receiver and the satellite that is communicating to the receiver. And um, the position of the satellite is known and broadcasted by the satellite. So based upon the range and the position of the satellite, the receiver is able to determine um, the possible locations where it could be present. And so that's the core idea behind it. And how the range is determined is based upon the same principle that is used in radars detecting aeroplanes at the coast or in the air. So the the the, there's a two-way path of a pulse in case of radar, and the time it takes for the the pulse to go to the target and come back is used to estimate the two-way distance, because we know the speed of light. And in case of the GNSS, the same principle is used, but it's one-way communication, because there is no two-way communication going on between between the receiver and the satellite. But once the range is determined and we know the location of the satellite, we can start estimating the location of the receiver. So here is an example. Let's say this is the location of satellite, and the receiver determines that it is 12,000 miles from the satellite. So the receiver can be anywhere on this sphere of the radius 12,000 miles if only one satellite signal was available. Now suppose that the receiver is able to have line of sight with the second satellite, and it gets its estimate of the location of the second satellite and its distance or range to be 11,000 miles. Now there are two satellites, two known locations, and distances from those two locations. So the only possible place that will satisfy those conditions will be the intersection of those two spheres, which will be a circle. So going from one to two satellites, we have improved our estimate of location from anywhere on the sphere to anywhere on the circle. Now suppose there was a third satellite that also became available, and now it will be the intersection of the three spheres, which will be 2 points. So the ambiguity between position will be only between these 2 points. So let's say if you had 3 satellites available, you could reject this point because this is not on the Earth and pick this point, and that would be the location. But to not to have this ambiguity, you need at least 4 satellites to pinpoint the location on the surface of the Earth. So 4 satellites, if you have 4 broadcast signals, you can pinpoint the location. But it will have uncertainty because 4 satellites signals may have issues. One of those satellite signal may be have some more noise, and that would reduce the accuracy of the position determined. Now, but typically more satellites are broadcasting, the more accurate the signal would be. Here are 3 examples of different GPS devices that you may come across, and they all will have some measure of accuracy provided on them. So in this case, you can see there is a signal to noise ratio, which means the strength of the signal to noise is 12 times greater than the noise. Here is another where there's a specification how many satellites are in view, and there's how many satellites are in the line of sight, and what is the relative strength of all those satellites. It even tells us that our accuracy right now is within 28 inches, which is pretty good, a couple of feet. If we go over here, it says plus minus 15 feet. So in some way you will see a measure of accuracy, which is in a way related to what satellites, how many satellites are being used to calculate that position. So here, this is a TerraSync software on a mobile device, and it even tells you that where are the signals coming from in the sky using a sky plot. And likewise, this is a Garmin unit, and it's giving a sky plot showing all the satellites and directions, cardinal directions, as well as the signals coming from all of these satellites and how strong those signals are relative to each other. So it is important for us to know the accuracy, because that means what is our position on the ground plus minus a certain number of feet or meters. So the signal error can come from various sources that can reduce our accuracy. So there can be delays. If the signal is coming from space, it passes through the ionosphere, and there can be delays in there. There can be scintillations that can deteriorate or attenuate the signal. There can be clouds in the way that can also cause scintillations. Below the clouds, we have trees and buildings that can mask the signal, which means the signal is the signal is obstructed. There can be other sources of signals in the neighborhood, and they can be, if they are the same frequency, they will be jamming the signal from the satellites. And lastly, if your receiver has electronic components like transistors and capacitors, they have noise as well. So that noise can also affect the signal. So all of these sources at the end can impact the signal and introduce inaccuracies that show up as an inaccuracy in the position with some bound of plus minus certain number of feet. So when we are looking at a GPS device, we will see accuracy in different ways. So there could be a horizontal accuracy separated from vertical accuracy, or there could be a single accuracy value lumped together. Now the software that you're going to use in the lab is called the GIS Cloud MDC, Mobile Data Collector, and there you will see an accuracy term on the main screen that will tell you the accuracy. One of the ways you can improve this accuracy is leave the device on the ground without holding it in your hand so it doesn't shake for a while, and as it gets connected to more satellites in the sky or starts receiving signal from more satellites in the sky, this number starts to go down, and once it is within an acceptable range, you can take the measurement.